I wanted to welcome you to the first online ZIO New York City meetup. We are extremely excited to have you all here with us. There's a lot of people joining and the numbers are really amazing for the first meetup. I also wanted to use this opportunity to thank our sponsor, ZIVerge, who helps companies thrive using competitive advantages of functional programming. So thank you, ZIVerge, for making this meetup possible. And today our guest is Adam Fraser. Adam is one of the core contributors to ZIO, a co-author of ZIO Test and author of ZIO Query, and also solutions architect at ZIVerge. And Adam will be speaking today about getting started with ZIO. So Adam, the mic is yours. You can get started. Thank you.
Awesome. Thanks so much for the warm introduction. So this talk's going to be a little more of an introductory talk. So really, if you've heard of ZIO, if you thought it was interesting, but you've heard a lot of things along the way about ZIO, about managed, about effects, about this and that, and you're kind of like, where do I start here? This talk is really designed for you. We're kind of going to go from the ground up and hopefully get you to a point where you feel comfortable diving into the code base and trying to write your first program with ZIO. As I mentioned a minute ago, we want to make this as interactive as we can. I feel like some of these online events, there's kind of people back to back every 30 or 45 minutes. And so you're kind of just trying to get through your content and you don't have as much time for questions and answers. And at least this time we kind of had the luxury of I'm here as long as you're willing to put up with me. So as we go through, if you have questions or there are things that don't make sense, just raise your hand, ask a question in the Q&A or in the chat, and we'll try to hit those as we go where it makes sense, or sometimes we may just kind of defer them to the end if it's less related to the content we're talking about right now. But with that, let me try to share my screen here. And this all makes sense. Sorry, just doing the screen share here. All right, can you all see my screen?
Yes.
All right, awesome. So 3 things I'm going to cover today. First, just an overall introduction to ZIO, what it is. We're going to talk about some of the basic data types and what this is all about, just so you understand kind of the language here. Then we're going to talk about some of the key concepts behind ZIO. And so I'm going to try to go through some of the features, but not just in a way where I tell you about this feature and tell you about that feature, but kind of motivate it from what are some of the underlying goals that we're trying to achieve here, so that as you're going through it yourself, you have more of a sense of what you can expect and where you might look to go. And then finally, we're going to talk about migrating to ZIO. A big problem that a lot of people have is they say, okay, this is fantastic, this is great, but I've got 10,000 lines of code that I've written in something else. And how do I start to make the move there to take advantage of the features that ZIO has in a way that is incremental and that lets me keep doing all the other things that I need to do for my business? So start out, ZIO is a library. So ZIO is a library for asynchronous and concurrent programming in Scala. So modern applications, we need to do things at the same time to take advantage of having multiple cores on our local computers, having multiple places that we can go for our compute, as well as needs to be concurrent, because any type of application we probably have all sorts of different requests coming in and we can't deal with them one at a time. We need to be dealing with them all at the same time and managing that, even though some parts of them are going on their own, some parts of them are interacting with some type of shared state, and all of that needs to be managed in a way that is reliable and consistent and works and scales. In addition to that, ZIO is the core data type in ZIO. So the core data type here is this ZIO REA. And you can think of a ZIO as a description of a computation that requires an environment of type R and is either going to fail with an E or succeed with an A. And so we'll break that down a little bit more in the coming slides, but a couple of key points there is it's a description. It's not a running computation. And we're going to see later on why that really helps us in being able to put building blocks together to build bigger programs. Secondly, it's potentially asynchronous. So this could be something that's just calculating number 42, but it could also be some program that's going to return at some point in the future, maybe is doing something over a network. It can describe all of those things. And so getting started, a good intuition is anything you're using a future or any type that's like a future, whether it's a Scala future or a Java future or a Twitter future, or anything you're using another effect system like a CATS effect or Monix, anything you're doing with any of those things, ZIO is here to help you with and is gonna, or at least trying to provide a better solution than everything else that is out there. So we got a lot of type parameters here with this REA and what is all of this stuff? And so a good mental model is this idea that a ZIO is some kind of, it's basically a function that's going to take an R and is going to give back either a success of an A here or is going to fail with an E. And that's not actually the way it's implemented because it's not stack safe, it's not performant, it doesn't handle asynchrony. But if you're just trying to kind of get a mental model as we walk through this stuff of what's going on here, it's a really good thing to fall back on. And we'll come back to that a couple of times. And so one of the really powerful things about this is, okay, we've got all those type parameters, it's a little scary, but we can use those to express a lot of more specific types that are also really helpful for us. So if we go back to that idea that we have this function that takes an R and is either going to give us back an E or an A, if we specialize that R type to be any, then we can always just satisfy that by giving it a unit value or giving it any other value we want. And so we can have this type alias and we can say that a IO of EA is just a ZIO where we specialize that environment type to any. And that's really helpful already because a lot of times we may have a computation that doesn't require any type of environment. And especially when we're moving from code reviews of the past, we didn't have an environment type before. So this is already, if we didn't want to deal with that R parameter, this is already making things more concrete for us. The other thing that's really powerful that we can do here is we can actually specialize that error type to nothing. And so we can have this idea of expressing a computation that can't fail. And that ability to control whether and to communicate with the type system, whether our effects can fail or not, is really helpful for us because we can know whether we've handled all of our errors or not. And if we haven't handled our errors, we can even know what errors are possible so that we can handle them in a meaningful way versus just always saying anything could fail with a throwable at any time at all. So how do we create effects? Well, we've got combinators to create effects from pretty much everything you could think of. So we can create effects from existing values. We can say ZIO.succeed 42 and just put a value that we already have into a ZIO. We can create them from side effects. So we could say ZIO.effect print line, and we can put any type of side effect in there. We can convert callback-based APIs into a ZIO with this effect async constructor. So this is really nice if we've got some kind of legacy API that expects callbacks and we don't want to really deal with that, even though we want to be asynchronous. We can just wrap all of those in a ZIO and deal with it in a much more straightforward way. You can deal with blocking effects with ZIO. So you could put in here something like reading from a file, and ZIO will automatically run that on a separate blocking thread pool to make sure that doesn't interfere with anything else you're doing. And you could also take a future, and we've got variants for all sorts of different JavaScript features, Java features, Twitter features. You can lift those into a ZIO. So lots of combinators for building these effects from basically anything you can think of. And then the other good thing is we can combine these effects together in very logical ways. So here we've got a very simple program here that I've got this get name function that's going to use the console service and is either going to give me a string or fail with an IO exception. And then I've got this say hello method that's just going to take a string and is going to use the console to print that out. And so I can use flatmap to glue these functions together to build bigger and bigger functions. And I can do, if I just want to transform the result, I can use map. If I want to combine different values sequentially, I can use flatmap. If I want to combine values in parallel, I can do zipper. A lot of other ones, but those are kind of some of the basic ones to think about, kind of starting to glue these things together into solutions for bigger parts of your problem. The other nice thing about having this error channel is it gives you a lot of flexibility in how you work with your errors. So if you want to handle your errors more explicitly and you say, okay, right now I want to do something with that error, I want to catch it or transform it, or maybe catch some errors but not others, I can use this either combinator to take that error and move it into the value channel, so that I can then do any normal combinator I want with that. But if I want to work more on the happy path and I want to say, look, I know this error could happen, and if so, obviously this is all completely pointless, but I want to proceed on the basis that I haven't failed yet, you can use this absolve combinator and take that error that you may have and push it back into that error channel. And that way you just have a successful value here, and you can operate on that with things like mapping it, just flat mapping over that success. And you still have that error there, you're still preserving that information, but you're not having to deal with that in every combinator you use. And finally, going back to what I mentioned before about ZIO being lazy, we're gonna say, okay, so it's lazy, it's just a description. How do we actually run the effect? And you can either run it by extending this ZIO.app, which just gives you this run method that you can implement, or you can use the runtime. So you just do runtime.default.unsafe_run, and you'd run your effect there, typically either at the edge of your program or at the boundaries between the part of your program that's ZIO and the parts of your program that are not ZIO, either yet or not ever going to be ZIO. So that's a little like high level of what is ZIO and what are some of the key combinators. Before we go on, maybe this is a good time to check. Does anyone have questions? Yeah, is there a way we can let him speak?
Yes, just a second. How do I do it? Where do I see who raised the hand? Yes, okay. Allowed to talk.
Hi, this is Raj.
Hi.
Hi, Adam. This is Raj actually. I have, I mean, it may be a very naive question, but you know, I haven't done a lot of, I mean, I've been coding in Scala for a long time, but I've never like done a pure functional programming. Okay, that's what I'm trying to be learning.
Sure.
When you say effects system, and when you say effects, I'm not able to, you know, what do you call, put some correlation in my mind. What do we mean by effects? I know that, you know, when you have a function, you pass a value and then you get an output, you call that as an effect. But is there any nice analogy and to keep in mind? And also, what is an effect system?
Yeah, absolutely. So you can think of all this in terms of, if we're saying pure functional programming, we never want to have side effects. We never want to do anything with our functions aside from returning values with them. So like 1 + 1, like, okay, we'll return 2. But the problem that we run into when we want to do kind of programs into large instead of programs into small is that for our program to do anything interesting, we've got to do things that are side effects. We've got to print things to the console so our users know what's going on. And we've got to do file I/O and network I/O and all these things that are definitely not just pure functions of adding different numbers. And so those are what you could call side effects of you've got some function that's doing something other than just returning a value. And so an effect system is how we manage those side effects by describing them instead of doing them. So to take a simple example here, and let me see if I can share my IDE here. Can you guys see this?
Yes, we can see.
Okay, perfect. So if I comment this out for a sec, and let's just do. So if I've got this here, this is great because I'm actually doing something, right? Like I want to actually say hello to all of you. So I need to do something that's actually going to say hello to you. But this right here isn't really a value. So if I do val say hello here, this is just a unit. I can't do anything with this. I couldn't like repeat it or handle some error with it or do anything with it. From a kind of value perspective, this isn't any different than that. The only thing this does is be a side effect. And so that makes it hard for us to manage and reason about our programs, because if this was like a network connection and this was just saying like connect to the server, if that didn't work and it just threw an exception, then it just threw an exception. I'm kind of SOL. I can't build anything bigger with that. Versus if I do the same thing and I make this a, and I make this a ZIO here. So now I'll say val say hello is equal to console dot put stir line hello New York. And now this thing is a value here. So if I don't do anything to run it, if I just make this a normal app, this isn't going to do anything when I run the program, because all this is a description. It's not going to do anything until I run it. And the fact that it's a description gives me a lot of ability to do different things with it. So I could do something like say hello twice is equal to say hello dot repeat schedule dot recurs 5, say. Twice, let's make this 2, so my name is not a lie. Actually 3 times because I recurred twice. So we can see here that because this was a description, I have a lot more ability to put it together with other things and control it. And this was kind of a simple example, but when we start doing things that get more complicated, having that ability to reason about our code gets really powerful. Does that answer your question?
Yeah, but in a way, yes. But you know, why do we call it as effect system is the point, right?
Yeah. So you can think of, we call it an effect system because it turns side effects, things that are not part of the return value of our functions, into things that are still pure values. So a functional effect is something that will do something at the end of the day, but that is still just a pure value right now. This is just a value. I'm just returning something with a function just like everything else. So that's what makes it functional. But when I go and I run it, I'm actually going to do something interacting with the world. I'm not just going to do math with it. So that's what makes it an effect. So that's why we call it a functional effect. So
you describe, and then you, at the end of the world, you interpret.
At the end of our program, we do, exactly.
Yeah, interpret. Okay. Okay.
Awesome. And is there another question from Yuri, is it?
Okay, we have some questions. Can you see them, Adam, in the Q&A section?
Yep, hold on a sec.
Quite a few.
All right, let's see. Okay, so we had a question about the benefits of referential transparency. Maybe let me push a little bit farther, because I think we're going to get to some examples that are going to highlight that. So parallelism, we're definitely going to get to that. And then we have a question, is there any problem with using ZIO nothing EA? Yes, so that's a great question. That's actually a great question to hit on right now. So the way to think about that is, we have this idea that we said ZIO REA is like a function R to either EA. So the problem with having nothing as the R type here is that we can never produce a value of type nothing. There is no value of type nothing. And so if you have a ZIO nothing EA, that's actually an effect that you could never possibly run, because the only way you could run it is if you could provide it with a value of type nothing, and there is no value of type nothing. So it could describe a very specific thing of essentially an effect that could never be run, but that's typically not very interesting for us, because we do want to have programs that we can run. So that's why we use the any type here, because any means that we can provide it with any value at all and run it, and we can make up the unit value, we can make up the number 1 or number 2 or anything we want, and we can get that if we're not using the environment type. So that's why we use any for the environment type instead of nothing. Okay. All right, so I'm going to keep going here, and I'm going to make sure I hit on the points about parallelism and referential transparency. And that's actually going to be a perfect lead up for us. Let me switch back to the slides here. Okay, can folks see the slides again?
Yep.
Awesome. Okay, so going back to that point we talked a little before, first key idea behind ZIO is that ZIO is lazy. So everything, just about everything you see, whether it's ZIO or other types built on it, is going to be a description of something that's going on instead of something that's actually going on right now. And that's important because, one, a common thing that I have people ask me is they're like, hey, my program doesn't do anything. And a lot of times it's because they've written the program, but they haven't actually run it. So easy thing, but when you're starting out, just make sure you either do that, you either use the runtime and you unsafely run it, or you extend apps so you're actually doing something to run your code and you don't just have this description or blueprint of what you do sitting out there that's very brilliant, but that isn't actually doing anything yet. So the second idea that is built on that and gets to that question about referential transparency is this idea that ZIO is composable. And so a big part of what we're trying to do is have all these little pieces that glue together in just the right way so that you can solve more complex problems on top of it. So here we've got an example where I've got this ZIO tweets that's gonna access some kind of online service and give me latest tweets about ZIO. But I'm connecting to the network here. This service might be down. We might be rate limited. Who knows what's going on? So this could fail. In this case, it could just fail to the throwable. But we want to make sure we still get all of our tweets to show people or do something with. And so we'd like to retry this operation. And ZIO comes with this data type called schedule that helps us model retries and repeats and build different, more complex schedules from simpler ones. So here we've got just one of the basic schedule constructors that's just going to retry whatever this is with an exponential backoff. So it's going to retry, it's first going to wait 1 second, then 2 seconds, then 4 seconds, and so on. And so just with this, we can see we've already done some reasonably complicated logic that with most other things would not be as concise or as easy to do as this. And one of the key things that enables this is that idea of laziness and referential transparency, because the only reason we can do this is that this ZIO tweets is a description of an effect. So like if you thought about ZIO tweets as being a future instead of a ZIO, then as soon as we touch this val, as soon as we created this val ZIO tweets future, it would already be off and running and connecting to the service and either succeeding or failing. And because it would already be running, we couldn't retry it at all because it's kind of already out of the bag. It's already doing its thing. It's not a description that we can do something else with. It's like already done. It's kind of like if we've got a bunch of eggs and we want to add some milk to them, we can do that. But if we've already cooked an omelet with the eggs, then we put milk on it, we're going to get a really weird breakfast. The next point here is ZIO is very aggressive about trying to preserve as much information as possible. And one of the ways you see that is with this error type. So here we've got a pretty simple example where we're just trying to load some configuration information. But we could fail in a couple ways. We're going to try to read this file, and we could have some IO error as we're reading the file. And then once we read the file, we're going to try to parse the string that we get from the file. And we could have some error where it's not in the right format and we're not able to get configuration from it, or we could get a configuration from it. And so the first thing to notice here is each of these can fail with a really specific type of error. So if we were using a future or most other systems out there, this would implicitly be a throwable, right? We would just have any future we have can, essentially as far as the types are concerned, fail at any time for any throwable. And so as soon as we create this, even if we know that the only reason this read file operation can fail is because of an IO error, as soon as we put it into a future, we just get a future that tells us, well, I could fail for any reason. And maybe when we have this read file operation, it's really clear to us, and we were the ones who wrote it, that like makes sense to us, and we know that like the error we need to handle is an IO error and what to do with it. But maybe we move on to other parts of the code, someone else is looking at this gets built as part of something else. We can pretty quickly get to a point where we don't really know why this could fail or what to do about it. And then we could have a situation where maybe we think we're handling all the errors that could occur, but we're actually not. So having this kind of typed error channel becomes really useful. And the other thing that's nice about this is the type inference is quite good here. So if we combine two effects that could each fail for some reason, the combined effect could fail for essentially the super type of the reasons that each part of it could fail. So here, if we're both reading the file and parsing it, well, we could either fail with an IO error or a parse error. And so this type's going to naturally be inferred as a config error, which again is preserving that information for us of, now if I'm looking at this signature, and maybe when I'm looking at it, I don't even know that a file was read here. I just know that this is giving me some configuration. Well, now the type signature is going to make really clear here that, hey, this is a config error. This could either be an IO error or parse error. And if you want to, you got to either accept that those errors could happen, or you've got to do something to handle them. And then what can, I think, even be even more powerful than this, especially starting out, is that idea that we can show that our effects aren't supposed to fail for any reason. So here I'm reading that configuration information, and then I'm using this combinator or else succeed that essentially is just saying, if this fails for any reason, then just use this success value instead, use this default configuration we have. And so now we've got an effect that can't fail at all. And so we know if we're dealing with this, all the errors have already been handled, and we don't need to do any additional error handling ourselves. And so ZIO's even got some functionality in it where if we try to use an error handling combinator on this, it's actually going to warn us that, hey, you're trying to use an error handling combinator on something that can't fail. That doesn't make sense. So really helping the type system work for us. All right, so concurrency. So someone asked the question about parallelism, and we talked about being asynchronous and concurrent, and we talked about a lot of stuff before this, but we're here. So ZIO has a very powerful fiber-based concurrency model. And you can think about fibers as lightweight equivalents of operating system threads. So just like a thread, they each describe a sequential set of execution logic that's potentially happening at the same time as other fibers with their own execution logic. But fibers are a lot more lightweight than threads. So you can have hundreds of thousands of fibers at a time in an application versus you would never want to have that many threads operating at the same time. And the other great thing about fibers is they semantically block, but they never block any underlying operating system threads. So when you do this join operation, your program logic is going to wait until this fiber is completed, but there's no actual fiber that's blocking. And as long as there's other work to be done somewhere else in your program, all of the underlying operating system threads are going to be doing all of those other things until this is done. So it's really nice for you as a user that you get the benefits of a asynchronous API that you would get if you were dealing with, say, callbacks, but you don't have to deal with having callbacks and callbacks and callbacks and plumbing that yourself. ZIO's runtime handles that all for you, so you can write code that looks very linear, but that has all these benefits for you. And in addition to having fibers themselves, ZIO's got a lot of powerful concurrency combinators built on top of fibers. So here we're looking at the ones for parallelism to get directly to your point. So pretty common thing is we might want to do a bunch of work in parallel and then collect the results. And so ZIO's got a very straightforward combinator for this for each par that just lets us perform an effect for each element in the collection. So here we've got these user IDs here, which we could imagine is just a list of users that we need to look up. And then this is an effect that's going to take a user ID and look up the information for this user. And without us having to do anything else, this for each operator is going to fork off a fiber to do each of these tasks, wait for them all to be completed, and then gather the results back together into a list. And it's also going to take care of a bunch of other things for us. If we're writing this ourselves, we might forget, well, what if one of these fails? Then we can't return the list we wanted because one of them failed. What do we do with all the others? Are they still running out there? And with ZIO, if there's a failure in one of these, all of the others are going to be automatically interrupted. So these combinators are building in a lot of logic for you where it's all based on fibers, but there's a lot of kind of thought that's been put into this to handle those things for you. And there are also a lot of nice variants of these for different use cases. So you might say, well, okay, that's great, but I don't want to be hitting this database with more than 100 concurrent requests. And so we've got this for each par n operator that is literally the same thing, except you put an n here, you put 100, whatever your number is, and that's going to limit the degree of parallelism here. We talked about parallelism. The other key part of that is concurrency. So here we're looking at an operator in ZIO called race. And so let's say that we've got some information we want to get. It's in both our East Coast and our West Coast data centers. We want to ask them both because we want to get this information right now. We want to get it from whoever's faster, but we also want to be efficient. So if the East Coast data center gets back to us first, we want to cancel that request from the West Coast data center so we're not wasting compute or wasting any more time doing that. And this race combinator is automatically going to handle that for us. We just put in these two effects. It's going to return the first one to succeed, and it's going to interrupt the other one. And again, lots of different varieties of that. If you want to race 100 different things, you can do that. There are variants if you want to get the first result, whether it's a success or a failure, get the first successful result. Lots of things that are there for you. And this really leads into the next idea, which is that ZIO is resource safe. So there's this operation on fiber that's really important and that you don't get generally on systems that aren't fiber-based, which is interruption. Fibers can be safely interrupted. And that's really important for safe resource usage because in just about any application, we have situations where we start doing something and then we actually don't need it for whatever reason. The user goes to the web page, they click on something, so we start processing some requests to get them what they want, but then they exit the web page. All sorts of situations like that. And for any of those, if we're still doing that work when someone doesn't need it, we're wasting resources. And if we've got a large application that we want to keep going for a long period of time, eventually, if we keep doing that, that's going to be a problem for us. So it's really important to be able to shut things down when we don't need them anymore. And this is something that, again, if you're not using fibers, you don't really have, where like if you think about a future doesn't have an operation to interrupt it. So if you're using future-based code and future does have an operation to do racing, like we just talked about, it's first completed of, but in that case, you're like taking that first completed of, and that second value that you're never doing anything with is like still spinning off there in space, potentially doing who knows what. So it's really nice having that. And it also adds a lot on top of what you can get with threads because it gives the ability to have finalizers. So you might be listening to what I'm saying so far and saying, well, hey, if I just have a thread, I can do thread.interrupt. I can shut that down. And you kind of can, but one, those threads are expensive to create. So it's kind of like you're blowing up the car to keep the car from doing something. It's like, okay, you stop the car, but the car was an expensive car. And two, you don't necessarily have guarantees that you're going to be left in a consistent state of that thread might have opened some file, but not yet closed it. And are we sure that we're in the state, we're kind of left in a state where everything that got cleaned up needed to get cleaned up? With ZIO, we've got very strong guarantees around that. So there's this operator called ensuring that says this effect, no matter how it terminates, whether it's successful, whether it fails, whether it gets interrupted, I want to make sure this finalizer runs when I'm done. And that's the basis for other combinators. Like there's one called bracket, it's used for resource usage. So the idea would be to say, like, I'm going to try to open this file. And once I open this file, no matter what happens, I want to make sure I close this file. And this is really important in combination with that interruption, because without having these operators, if you just have things like try catch, you don't have safe resource usage when you can have interruption. And the thing that builds on this even more is this concept called a managed resource. And so you could think of a managed resource as taking the acquisition and release actions for some resource and bundling it up into its own data type. And you can put these together in all the same ways that you can with a ZIO. You can put them together by flat mapping them to do it sequentially, you can do it in parallel. But what this does is it lets you put logic together for acquiring and releasing multiple resources and do it in this very simple way. So here we've got a situation where we want to use this Postgres database, but to use it, we need some kind of connection. And so both of these are things that require some kind of acquisition release of, we've got to open this connection, we eventually have to close it. We've got to open this database, eventually we have to close it. And all of this stuff, we've got to make sure we do no matter what. And we've also got to make sure we do it in the right order of, I've got to open the connection before I open the database, and I've got to make sure I don't close the connection before I close the database, because then I got no way of making sure I close the database. And you can imagine this would be something that normally you might need to have a decent amount of logic to make sure that all of this worked the right way. But with this managed data type, all of this is done for us essentially automatically, where when we just put these two resources together with this flat map, we're guaranteeing that they're going to get acquired in the right order, that they're going to get released in the right order, and they're going to get released no matter what happens. And you can see how that starts to fit together with some of the other things we were talking about of, if we went back to our race example, we had these two different data centers. Well, maybe the thing that we're racing is actually establishing the connection and then establishing some database connection at the data center. And again, whichever one gets interrupted, we need to make sure the whole thing gets shut down, and we need to make sure it gets shut down in the right order and reliably. And you start to put these pieces together, like problems like this get really, really simple to solve. Maybe before we keep going there, shall we do another check-in for questions?
Yeah, there's quite a lot out there. Didn't want to interrupt you.
Yeah. Okay, so I think we hit on the benefits of referential transparency. If that's still not clear, we can definitely come back to that. I think we talked about parallelism. So does ZIO provide some sort of synchronous execution like Monix coeval for writing tests when using tagless final? So ZIO can manage, can model synchronous computations. Typically that's done not through a separate data type, but can be done either through controlling the executor that's used. So for example, using a single threaded executor or by the test framework itself. So we use something, we have something called ZIO Test. That's kind of the ZIO version of a test framework. And we've got some specific combinators in there that let you perform tests sequentially or things like that. But I think the other thing I might emphasize there is I think sometimes there can be a little bit of a risk to testing code that's asynchronous synchronously, because you may not be identifying all of the different execution paths that can occur. So that would just, I think, be the other watch out there. But I'm not sure I answered all of your questions. So if there's something I didn't hit on, we can definitely come back to it. Okay, so we've got a question from Raj. Why is it called for each par instead of mat par? For each sounds side effectful. And so the reason for that is that for each par is the closest that we have to side effecting in functional code. So we're doing this functionally, so we're not going to actually do side effects, but that thing in the for each, it's an effect of the thing we might be doing in there is connecting to some kind of database. It's not just solving math problems. So for each, we feel, is actually a pretty logical analogy for, especially for people who are coming from an imperative background of you're doing some effect, you're doing it in a ZIO way, but you're doing some effect for each thing in that collection. So then you say, are there any complications when it comes to measuring performance with laziness? There can be some. So I'd say there are two maybe performance aspects to think about. So one is just what's the actual performance, and there's definitely some overhead to the ZIO runtime. So don't use it for things that don't need it. You know, if you're doing some tight loop of just local computation on your machine, that can all be put into one ZIO effect instead of kind of every round of your loop being in separate ZIO effects. But generally that ZIO runtime is really highly optimized to be as fast as it can be given what it's giving you, and stacks up pretty well against everything out there. Like, it's definitely a lot faster than Scala futures. So I think as long as you're using it smartly and you're not kind of doing tight computation in different ZIO effects, you're fine there. And then as far as benchmarking, you do need to be a little bit careful because there's some time in just essentially spinning up the runtime initially. So some benchmarks, you need to make sure essentially that you do the effect a bunch of times within one larger effect you create versus kind of creating the runtime each time, or you end up measuring more creating the runtime than how long the effect took. Okay, so looks like managed and bracket are sort of the same thing. So you are 100% right there. They are very similar. And the way you could think about it is that a managed is turning bracket into a data type. So bracket itself is just a combinator on ZIO that says I have one effect, and here's the action that's going to acquire it, here's the release action, and here's what I want to do with the resource between the acquire and the release. So that's a single effect that describes one acquisition release, but once we kind of put into that combinator, it's just a ZIO. So we don't have the ability to compose that with other resources that also require acquisition and release and have that logic weave together so that all of them get acquired and released safely together. And so that's essentially what managed does, is it takes the acquisition and release parts and bundles them together. And then with that, we can glue different resources that all require acquisition and release together to get a new resource that describes acquiring and releasing all of them. Okay, so next one is, since ZIO is declaring the type of failure results, what would happen in case of throwing exceptions? Yeah, so that is also a great question. So ZIO has something called the die error channel. And what that's for is exactly what you're talking about. Of whenever we write some program, we have some set of errors that are kind of the errors that are supposed to happen. Of I'm reading from a file, I could have a IO exception. But the reality is, while I'm reading the file, I could spill some Coke on my computer, and then whole thing's going to blow up for who knows what reason. So that's what that die channel captures, and that can have essentially any throwable inside it. And we find it's very helpful to separate the two because it really lets you distinguish these expected versus unexpected failures and kind of program for the things that are actually likely to occur and that you can do something about. So yeah, if I spill Coke on my computer, like I'm probably SOL, like who knows, I'm gonna have an out of memory exception, who knows what's gonna happen, and the whole thing's gonna come down, and there's not a whole lot we can do to manage or recover from that. But if I have an IO exception when I'm reading a file, well, that's a much more anticipated error, and maybe there are a bunch of things we're going to do. Maybe you want to prompt the user and say, hey, are you sure you gave me the right file handle? Or maybe we want to retry, or maybe we want to load a backup config. So one of the arguments I hear a lot about why people just have throwable for the error channel is this idea that kind of, well, you've got to mirror the operating system, and ultimately things could fail for any reason. And there's a grain of truth to it, but it's kind of conflating two different things of yeah, I could get hit by lightning when I walk outside my house, but every time I meet up with someone, I don't tell them, oh, I might get hit by lightning. But if I might have a work call or something, then maybe I'll say hey, maybe I'm gonna try to make it to dinner, but maybe I can't because this is gonna come up. All right, next one. So it might be faster if I come up with my own loop and then wrap the result in a ZIO effect rather than using the built-in methods like iterate and loop. So I think the question you should ask yourself there is, are you doing effects in each step of that loop? So if each step of your loop is trying to connect to a new data center or trying to open a new file, then those ZIO combinators are fantastic and are exactly what you need. If you're trying to compute the 50th Fibonacci number or something, you should do all of that in one ZIO because you're doing local computation that's not actually performing side effects that you need the capabilities of ZIO to manage. And you're going to be doing that faster if you do that all inside one ZIO effect. And then next question here is about streams. So I'm going to briefly hit on that. So there's a separate ZIO stream library that provides a ton of functionality that's based on that and is very tightly integrated with ZIO. So it provides both a really nice experience as well as really strong guarantees, since the streams are able to build on these concepts like bracket and manage to make sure that resources are safely acquired and released. Itamar, who's one of the other core contributors to ZIO, is the mastermind behind that. So he's got a bunch of talks about that. If you haven't, definitely check those out. Or I'm sure he'll be doing more talks soon. But yeah, really, there's a lot of cool stuff there. So I think the performance comparison between ZIO streams and FS2, I'm gonna punt on just because I'm a little bit less, not as close to that. So I'd encourage you to follow up on the Discord about that, and I'm sure Itamar can get you kind of the numbers on that. Any other questions? I probably went through those quickly, so if I didn't fully answer your question, feel free to raise it again. Okay, well, maybe we will keep going here then. So we talked about resources. Next thing that I want to talk about is testability. And so this is where we're going to come back to that R parameter. I kind of showed you a little bit about the R parameter at the very beginning, and then I kind of gave you the type aliases and hid it away. So we're coming back to that now. And so remember, the R expresses the dependencies that our program has. So we might need a console service. We might need a database. We might need authorization. We might need logging. We might need 10 different things. We might need persistence. And this R type is the way that we model all of those things. And you can really think about it as having these two fundamental operations. So the first is this ZIO.environment. And this lets us add a dependency to the environment. And so in a way, it's like conjuring something out of the ether of I'm saying, I need to do something with the logging service. So I'm going to do ZIO.environment logging. And I'm going to get an effect that requires a logging service and just gives me the logging service back. So this is kind of like an identity. Like if we go back to that, it's a function from R to either EA. Well, this is just take the R and put the R into the right side of the either. But actually really useful, because if I do ZIO.environment logging, then I've got that logging service here, and then I can call logging.logline or whatever other whatever methods I want to have on that service. So that's how we introduce dependencies into the environment. And then the other key combinator is this one called provide. And so this just says I've got an effect that requires an R, and I'm going to give it an R. And so if it required an R and I gave it an R, then it doesn't need anything anymore. And so I just get back that IO type where that R is now any. So this would be like down maybe lower down in my program, I said, I need a logging service and I'm going to do some logging with it. And then at the top of my program, I can just do provide logging service. And then I've got a program that doesn't require anything else and is ready to run. And so this ends up being really, really nice because it essentially provides a solution to the dependency injection problem of, I'm using something way down into my application, but I don't want to hard code it. I want to be able to provide different implementations, but I don't want to do all the plumbing of getting it from the top of my application 10 layers down. And there are other ways to do that. You could try to use implicits, but then your code gets a lot harder to reason about. You could use specialized dependency injection frameworks, but those kind of work as long as they work. And then when you kind of do something that the magic doesn't quite support, it can get very hard to do it with. You can try to do something like the cake pattern, but like none of them are great. And I think the other thing that's really nice about this relative to like tagless final is it makes it really easy for you to combine multiple services. So like if you have a tagless final style, at first it seems really nice if you say like, okay, logging is going to be one of my things, and I'm just going to kind of say I need a logging capability. But a lot of times our applications actually need like 10 different capabilities. And so suddenly we've got a point where every method signature I'm doing, it needs logging and persistence and Redis and network connection and this and this and this other thing. And I've got kind of like 10 different constraints, and all my method signatures get like super painful to write. Whereas because this is just a type, I can create any type alias I want for it. So if I require 10 different services, I can just say type my environment equals logging with Redis, with persistence, with this, with this, with this. And then I can just use my environment everywhere. So it provides a really ergonomic and nice way to get our dependencies to where they're needed. The other cool thing about this is that type inference works really well for it. So here we've got a simple example where I'm writing a little alarm app. So I'm going to read a line from the console, and I'm going to parse this to an integer. And this is just going to be how many seconds I want to sleep for. And then I'm going to use the clock service to sleep for that long. And then I'm just going to say, wake up. And so here I've used both the console service and the clock service. And here I've given the type signature just to make things clear for you. But if I deleted this whole type signature here, this type would still get inferred to be clock with console. So just like we saw with the error type, if I'm putting two effects together and one effect could fail one way and one effect could fail the other way, I'm going to get an effect that could fail either way. And similarly, if I put two effects together where one effect requires environment type A, one requires environment type B, when I put them together, I need both an A and a B. And so it really helps you see what your effects depend on. And then the other thing that becomes really cool about this is that it's really easy to provide different implementations of this. And so those could either be different live implementations used in production, or commonly a test implementation. And so here we're looking at an example where we're using a couple of the test services that ZIO Test provides. And so we're going to take exactly that same alarm app that we looked at before, which, you know, if we use the normal clock and console would be completely untestable because we're using real time and we're getting console input and output. But here it actually becomes really easy. The test console has this feed lines method that essentially just lets us give a line that would be the equivalent of the user providing their input. Then we run the alarm effect. Then we use this test clock adjust. That's not going to use any real time, but that's going to simulate the effect of time advancing. And then we get the output of the test console, which is going to have whatever was printed to the console as part of our effect. And we can just assert that that's equal to that wake up message that we were supposed to get. So it can make it really easy for us to test our programs. Next point would be ZIO's focused on helping you solve your problems. So I think relative to some other libraries, we're less about saying, well, this is like the principle of exactly what we should do, or we're focused on being minimalist, or we're focused on having this role. We're focused on helping you solve the problems that you deal with in this domain of asynchronous and concurrent programming. And so we're going to try to give you everything you need to do that. So far, we've really been focusing on that ZIO data type, which definitely is kind of the key and most important thing to understand in ZIO, but there are a ton of tools that are built around that. So there's something called a ref, which is the ZIO equivalent of an atomic reference. So lets you safely, concurrently update it, and actually has a bunch of cool functionality built on top of it where you can even transform the type of the ref. You can create refs that are read-only or write-only. You can drill into the type of the ref. A lot of neat things you can do there. Got promises, which is similar to a Scala concurrent promise, but essentially one value that you can set that you can wait on. Difference versus using promises completely non-blocking. Queue, also completely non-blocking. Read and write multiple elements. Also got a lot of neat things to it where you can even transform the type of the values that go into and out of the queue. You can attach effects to reading or writing from the queue, like you could log every value that gets written to the queue if it comes out of the queue. Semaphores for controlling levels of concurrency. And then that schedule data type that we talked about before that gives you a lot of ability when you do need to do retries or repeats to put those together in a really composable way. So you could say, before we just looked at like that schedule exponential, but you could say, do an exponential back off until I get to a minute, then repeat every minute 10 times, then repeat an hour 5 times, and then be done. And each of those would just be essentially one thing that would be very declarative. You wouldn't have to build in any of that logic yourself. Another thing that ZIO includes that can be really useful when you need it is software transactional memory. So this is basically solving the problem that if you think about something like an atomic reference, itself is safe for concurrent updates because it's atomic. But if you have 2 refs that you want to update, there's no way to put those together atomically. And STM lets us solve that problem. It gives us different pieces that we put together that as long as we do them within this STM data type, we can do multiple things atomically and build them together into one thing that will be done atomically. And that's supported by this retry operation that essentially the logic is that just like with like an atomic ref in Java, if something changes, we're just going to go back and we're going to retry the transaction. And this can be really, really useful when you want to solve more complicated concurrency problems where there's not something out of the box for them. So for something I was doing a couple weeks ago, I needed a priority queue. So we talked about that ZIO queue type that was, and I needed an effectual one. I needed one where I could have concurrent processes that were taking values from this, that were suspending until a value was available. I needed all of that functionality. And ZIO's got a queue, but it's not a priority queue. So it's kind of like, okay, what are we gonna do here? Because I need this thing, but it's like, it's not really an easy thing. Like it's not something I want to implement myself. There's a lot of like optimizations and issues that go into like that implementation of the queue to make it as efficient as possible. But STM provides a really nice solution for this sort of thing where this is like basically just on this page is like the code to essentially do it, where I've got this T priority queue class I created. All it does is it wraps this T-ref, which is it's a transactional ref. So you can think of it as just like an atomic reference, but it has this STM capability where you can put things together. And internally, it's just going to wrap this sorted map. So this key is going to be kind of the ordering of the priority in the queue. And then we might have different values with the same ordering. So this is just going to be a list that has at least one value in it of all the values that are at that priority in the queue. And so I can just implement kind of key methods for a queue of offering and taking. So when I offer to the queue, it's really easy. I can just use this update method. And if there's already something with that priority, then I just add it on. And if there's not, then I create a new entry for it. And then this take is where you start to see some of that STM functionality, where I said one of the things I need is I need things to suspend until there's a value in the queue. I need that ability to kind of wait for a value in the queue. And so here I'm going to say, well, I'm going to get the value of this ref. And then I'm going to look at it. And if there's nothing in here, if this is an empty map, then I'm going to retry. And this retry is very smart, where it's not going to do some kind of busy loop where it's going to be using up a ton of CPU. It's not going to retry at all until this transactional variable changes. And then it's just going to retry this whole thing. And so the effect of that is that in a very efficient way, this isn't going to proceed until there's a value to take from the queue. And then it's going to take a value from the queue. And notice here too that like here I did ref.get, and then here I did ref.update, but I'm not doing this whole thing within an update. So normally we'd say, whoa, watch out here, Adam, you're creating a concurrency bug. But because we're doing this all in the STM context, this is okay. I can put all these things together. And so just with this code, I got this priority queue that I could now use in an effectual context. And if I wanted to, I could provide an interface where I run these things back to a ZIO. And so my users wouldn't necessarily even have to know that I used this STM functionality. I could just run these to a ZIO effect, and users wouldn't know the difference. Maybe at some point I do refactor and I don't use STM, but it gives a really nice way to kind of quickly build additional concurrent data structures or to solve concurrency problems that otherwise could be really tricky. So streaming, I'm just gonna hit a bit on, but I wanna make sure you know it's out there. So ZIO Stream is a pull-based streaming library that's deeply integrated with ZIO. Ton of combinators there, a lot of functionality for both streaming in general, safe resource usage, and one of the things it can be particularly good for is really you can think of ZIO as modeling single effects. So like before we talked about that effect async that would translate a callback-based API into a ZIO. And that would be used if you had an API that was going to call your callback once. So that ZIO effect would complete with a value as soon as that callback was called. But sometimes we have interfaces where they're going to call the callback more than once. And that's a great case for streaming. So like here, we're using this effect async constructor on ZStream that is going to give us this callback that in this case can be called multiple times. And so we're going to register ourselves with some Twitter feed, and we're going to say every time we get a batch of tweets, call that callback with the tweets. And then we can operate on those in a very declarative way of we can say, well, let's filter for everything that John posted. Let's just get the text. As a side effect here, let's log these to the console just because we want to see them right now. And then let's write all these to a file. So I think it's really good for streaming problems in general. And I think sometimes when you have problems with ZIO that seem challenging with ZIO, I think sometimes moving to a streaming solution can provide a very elegant approach to dealing with them. And then the final thing at this point is there are a lot of other libraries that are being developed around ZIO. So some of these you may have heard of, and I'm definitely not doing justice to all of them, but I just want to kind of give you a sampling of what's out there. Caliban is a really fantastic library for GraphQL that a friend of mine, Pierre, has worked on. Leverages Magnolia to automatically drive your schema for you. So a lot less work in kind of exposing your data with GraphQL than with other solutions that are out there. ZIO Kafka is a Kafka solution that's based on ZIO streams. ZIO Config gives you a way to load configuration data for ZIO programs. ZIO Logging, as the name implies, does logging for ZIO programs. And all of these applications are able to take advantage of some of the features we've talked about. So like if you think about ZIO logging, that logger is going to exist in your environment type. And it being there is going to give you a very ergonomic way to kind of say, I need to have logging, and to make it pluggable so you're not just hard coding one type of logging, but to pipe that through your program in a very simple way. ZIO Kafka is taking advantage of that functionality of ZIO streaming, the polymorphic error types. So all of these things are really benefiting from the additional functionality that ZIO has, as well as I think there's been a good development of people trying to have a relatively consistent interface in terms of the way type parameters are listed, the way methods are named. So I think you'll find that as you learn about ZIO and you go through some of these different ZIO libraries, things are going to be very familiar to you. So you get a pretty high return on your investment in kind of learning about this stuff because you can leverage it across these different libraries. Shall we pause for questions there again?
Yeah, there's quite a few again.
Scala test versus ZIO test comparison. Okay, well, I'm definitely the right person for this one. So what you're lacking with just about every other system is they're not treating effects as first-class values. So if you think about Scala test doesn't really have any concept of ZIO, or whether it's ZIO or whether it's Monix or CatZIO or any of these things. Like, the best it's going to get to is a future, which is really you could call it a quasi effect, because the future is a running computation versus a description of a computation. And so essentially what that means is, if you're using any other system, every time you do a test, you're like unsafely running your whatever it is you're testing, which, besides just being kind of annoying, actually makes it harder for you to do a lot of things. So like a pretty common thing in tests is you're going to have some kind of resource that you want to use. And just like before, we want to make sure we open the resource before we do our test and we close the resource after. And maybe we have different resources that we need to put together in the right order. And so in ZIO test, that's all really, really natural, because we have this managed data type we talked about, we have bracket, and all of those things just naturally fit together. Whereas if you're doing it with something like Scala test, like that has to become this whole other concept of kind of fixtures and setup and tear down, and none of that knows about any of these functional effects either. So like you can kind of set up and tear down, but you definitely don't have any of this logic that, like, let's say I just want to interrupt my test. I just want to Control C and shut this down. Is that connection actually going to get closed? Probably not. Another example would be like timing out tests. Like in one of these other frameworks, you can kind of quote unquote time out a test, but all you're doing is just like failing the test and moving on. If that test was doing some work in the background, then that would still be happening because you don't have a way to interrupt a future. But with ZIO, that interrupting or timing out a test gets tied into ZIO's whole interruption mechanism. And so you get all the safety and the guarantees from that. So next question is, how is back pressure handled in ZIO? So back pressure is more handled in ZIO stream versus in ZIO, because I mean, please jump in or ask more questions if you feel like I haven't addressed this, but I think back pressure is really more of an issue with streaming frameworks, and it's addressed in two ways. So one is that ZIO Stream itself is a pull-based framework. So if you're pulling, then you don't need to back pressure yourself. What you do need that for is when you interface with a push-based framework, and that's where that queue data type comes in. Because essentially that queue has the ability to do some back pressure there. ZIO by example. I think that's a fantastic idea. I think I don't think that quite exists today. I think there are different efforts in that direction. So I think there are a lot of like good blog posts people have done and things like that. Wiem, who I saw at least on the list of attendees earlier, has written a bunch of great stuff there. But there's no kind of one place that like tries to kind of build up from that. So I think if anyone is interested, that is a fantastic project that I think there are a lot of people who would love to see and would love to support you and help you out with. And I mean, it's a great idea we should do in general. I think we try to do a lot of work on the documentation, but we also, I think, add features pretty quickly. So sometimes it's a race between the features and the documentation. Can you use partial functions with collect in this case? I'm not sure exactly what example this is referring to, but in general, Yes, there are a bunch of different ZIO combinators that work with essentially that are called collect, or that are called variants of collect, that let you do collect-like things with effects instead of with traditional collections. So yes, 100%. And actually, one of the really nice things there is using that error channel, because if you've got that possibility that just the function isn't defined, you can move that between the error and the success channel. So you could change your error type to be like option of E instead of E, and then you could have A instead of option of A, and it can make it both more efficient and more ergonomic to work with those sometimes. Is there a Scala.js version of ZIO restrictions? Yes, there is. Very minimal I mean, basically, I think the only restriction is that we can't do things that are essentially impossible to do on Scala.js, which basically means we can't block. So there are a couple of methods of, like, on the JVM, there's a unsafe run method that, like, at the end of the world runs your program and returns your result synchronously, and actually, like, waits for the result, because you're like finally doing that. Which you can't do on Scala.js because you can't block. But other than, like, very limited examples like that, everything is supported on Scala.js. Like, all of the CI is run every day on Scala.js on 2.11, 2.12, 2.13. So yes. Is ZIO Test an independent test framework? Could it be mixed into Scala Test? It is a separate test framework. I don't think it could be mixed in with Scala Test, because essentially it does the same thing that Scala Test does. So it's kind of at the same layer of being a solution. What are the main differences between ZIO, CATS, and Scala Z? So I'll talk more about CATS versus ZIO, because I think there's less development, particularly around effect systems for Scala Z. I mean, ZIO kind of was supposed to be the next generation effect system for Scala Z. So I think at this point, it's more basic functional programming abstraction. So it's kind of the foldable and monad and functor and all of that stuff, which is kind of great in its own way, but solving kind of a different problem than ZIO is trying to solve. As far as CATS versus ZIO, I mean, I'll kind of, obviously you're getting a biased perspective from me, and I'll try to take it from my perspective. I think one key difference is that, and let me maybe step back and just talk about kind of what CATS is and how they fit together. So CATS is kind of three different things. So one is it's a set of basic functional programming abstractions of that kind of same Scala Z thing of the monads, the functors, all that. So that part's just kind of a different thing. The part that is more overlapping with ZIO is CATS effect. And that itself is actually kind of two different things. One is you could kind of think of it as like a protocol for functional effect systems. And then second, they have their own specific data type of CATS IO. And so in terms of being a protocol, there's a ZIO interop CATS effect package that works for ZIO with that same protocol. So if for some reason you do feel like those CATS effect data types are great and you want to use those, you can still use those with ZIO. We would say that ZIO is the best concrete data type to use with CATS effect. But I think there is some limitation there that it's a protocol. And so if you work at that protocol level, you essentially don't get access to any of the features that ZIO provides that are more advanced than what the protocol provides. So if you're just using ZIO through CATS effect, you don't get the environment type. You don't get the polymorphic error type. You don't get any of the specific combinators that are implemented on ZIO to make it more convenient to do specific things. So if you're going to go that way, great. And from my bias perspective, you should use ZIO as your concrete data type. But I think you'd be better off with just going ZIO native. And I think the other thing you get there is just it becomes a lot nicer to work with because you don't have all these higher kinds of types that make the type signature sometimes hard to reason about, and also can make type inference worse. Yeah, that's, and then I think maybe just the other thing I would say is that idea of, I think sometimes there's a push and pull for Cat's effect of some of their philosophy is like they want to be the quote unquote like minimal solution for being effect and kind of let other people build on top of it, which is fine as far as it goes. But at least my view is like a lot of times as users, like you've got problems to solve and you just want to solve your problems and you want something that's going to fit together and like do that for you. Like you don't really care about like, someone's philosophy of minimalism or not. And so I think with ZIO, you get a lot more in terms of having a integrated solution, and one where I think the attitude is more like if you come to our Discord, like if there is some like you say like, oh, this method would be useful, like if there's some basis for it, like someone's probably going to add it within the next 3 days or something. Versus I feel like if you kind of go to Cat's effect, you're going to get a lot more of like, well, is this really basic or not? Is this fundamental? Should this be here? Should it be somewhere else? And again, you just got to kind of pick what you want there. What about Scala native? So there's been some fantastic work by some of the Scala native contributors to get ZIO supported on Scala native. So right now they've got it compiling. I think they've got the entire ZIO test suite passing, except for like 20 tests, which out of probably more than 1,000 is pretty good. So it's coming. I just really like to, I mean, I'll take every opportunity I can, but I think the folks who are working on Scala native really done a fantastic job working on that, and really a great set of folks. So right now it's still experimental, but hopefully it'll be coming soon, and we're excited about that. Okay, well, I know some of you are probably getting bored of hearing me, so luckily we're at the last part of the presentation. And this is shorter. So hopefully all this has been enough to get you interested in ZIO. But there's this challenge of you've got a lot of legacy code. How do you move it to ZIO in a way that makes sense and lets you take advantage of the features, but also isn't overwhelming and lets you keep doing other things with your code? So I've helped several people migrate different projects to ZIO or add functionality, modules for ZIO. So I'm going to try to share my experience on kind of what works here. And it's really these 5 steps. So start small, run your effects, use type aliases, take advantage of the interop packages, and ask for help. So first one is start small. And so this is basically your like your game plan for migrating. And what you want to do is start by picking one part of your code base. And your goal is to make that your like island of ZIO in a sea of whatever else, a sea of futures or Monix or what have you. And so that like island initially, any inputs to that part of your code base from other parts of the code base that are in one of those legacy types, you're just going to lift into ZIO using one of those constructors we talked about. And then the outputs, you're going to run to that legacy effect type, either using some of the basic combinators in ZIO, like unsafe run the future, or using some of the tools in these interop packages. And so by just starting with that small part of your code base and using that lifting and running at the edges, you can pretty quickly have a situation where you've got at least some of your code ZIOified, but everything is still working, everything is still running. And then once you do that, you can slowly push those boundaries out of saying like, okay, that little island of functionality, that little system I migrated interacts with this other system. Let me move this system over. And then that kind of boundary where it used to be unsafely running your code now just becomes you're going from ZIO to ZIO, and it just all works. And you kind of push your boundary out a little bit. And you do that gradually over time. And I think if you're able to do that kind of incremental migration, it makes it a lot easier and more manageable to make the transition. Second piece of advice is don't be afraid to use unsafe run. I know we call it unsafe run because we want it to sound scary, and I think we do a lot of talking about what the ideal way is to do things, and the ideal way would be that everything is just a ZIO until the very end of your program, and then you kind of call run once to run your whole program. And that's definitely, like, in a perfect world, that's where you want to go. But the reality is, if you're coming from, if you're using futures today, 100% of your code is quote unquote unsafe. So as you're transitioning, don't be afraid to use that functionality. In fact, it's basically what you're going to have to do at the boundaries of that island of ZIO code you've created. So that's natural. That's kind of part of the process. Over time, as those boundaries go out and out and out, those uses are going to become fewer and kind of are going to move higher and higher up in your application until hopefully they get to the very top of your application. But it's okay to be doing that. The one thing that will help you there is try to create that runtime once at the top of your application that's kind of got like the thread pool, some of the underlying resources that ZIO uses. So generally, if you create that once at the top of your application, that's going to be the most efficient thing. I guess the one other thing to watch out for here would be aware of what effects are blocking effects versus are not blocking effects. Some other frameworks, like let's say Futures, uses an unbounded fork join pool. So it's, I think you can sometimes have less visibility into, or matters less if something's blocking. It's not the greatest if you kind of do a blocking effect on a future, but it's probably not going to be the end of the world. ZIO is pretty dichotomous of, it's got a kind of core thread pool for its asynchronous operations. That's typically the number of cores you have on your computer. And then it's got a separate blocking thread pool for blocking code. And so putting blocking code on that default thread pool can really impact your application. So there's that effect blocking constructor. Make sure you use that if you have code that is blocking. Next point would be use type aliases. So especially when you're migrating initially, those type aliases can be really useful. Most systems that you would be migrating to ZIO from, I don't really think any of them are going to have a environment type, unless maybe you're doing something fancy with reader T monad transformers. And you probably are using throwable for your error type, again, unless you're doing something fancy with like either T monad transformers. So this task alias that ZIO has is probably going to be the closest thing to what you've been doing in the past. It doesn't have an environment type. It could fail for any throwable, and it's eventually going to produce an A if it doesn't fail. And so a good approach can be make everything a task initially. And then you're going to have less work to do because things are going to be most similar to what you're doing today. That'll help you get kind of that island of ZIO code going and grow that. And then over time, as you do that and you get more comfortable with ZIO, then you can evolve it to take advantage of some of the other functionality that ZIO has. So once you've got a set of code that's all using tasks, then you can maybe start to ask yourself, well, maybe there are some cases where I'm using tasks where my effect can't fail at all. Can I use UIO for that? So I can actually prove and tell myself that an effect can't fail. Or maybe I can get more specific with my error type. Maybe it's not actually just any throwable, maybe it's some specific subtype of throwable. Or maybe in this part of my code, does it make sense for me to create my own domain-specific error type and my own hierarchy of how things can fail? And then typically even after that, you may say, well, how can I take advantage of the environment type for dependency injection? And what am I doing right now that maybe I can refactor into a service that I can pass around my code and just use that environment type for it? But again, I think taking that incrementally and not saying like, you know, oh my God, there's all these things, I've got to do all these things right now, is going to make it way easier for you to start using ZIO and start seeing the benefits and build support for it. And as you're doing this, take advantage of the interop packages. So there are a bunch, I think one thing ZIO is really strong on is interoperability with other frameworks. So Scala futures, you can create a ZIO from a Scala future, you can run a ZIO to a Scala future. There's also the same thing built in for Java futures and all the different varieties of listable futures and completable futures and all those. There's an interop package for Twitter futures. There's an interop package for Monix. There's an interop package for Cat's Effect. For the streaming folks, there's an interop package for reactive streams. So I think for just about anything that you're likely kind of coming from, there's something out there to make it easy for you to convert that thing to a ZIO and convert a ZIO to that thing. And so take advantage of that for those edges of the ZIO part of your application. There's already easy stuff for you to do to kind of translate to and from at the edges of your island there. And then finally, reach out. I think the ZIO community is super supportive. Visit us on Discord. There's a really active discussion there. I think there are a lot of people who are super excited to get feedback, to answer questions, to help you out. Also ask at events like this. You may be bored of me by now, but I'm happy to answer questions as long as you would like. And then finally, ask for more of what you'd like to see and what would be helpful to you. I think one of the things we really want for this meetup is to not just be something where you kind of come once a month and someone talks at you, but something that's more interactive where we can have discussions. Maybe I've seen some things about like Python, they do like project nights where it's kind of weird with the coronavirus and everything, but I mean, maybe we all just kind of say on Friday night, we're going to work on our own projects hop on Discord, and if people want to, they can pair a program together. If there's other things that would be helpful, we want to be here to support you. So love any and all feedback. And with that, you made it. I really thank you all for attending, especially our first talk and taking the time out of your day. Thanks, Sandra, for doing an amazing job of organizing this and making this possible.
Thank you.
Thanks to all the ZIO contributors. I think we're up to like almost 300 people who've contributed to the ZIO core project, which doesn't include a lot of the other things in the ecosystem. There are so many things going on. There's more than anyone can do. So if you have any interest in contributing to open source, even if you've never done it before, even if you haven't done functional programming stuff before, please come on the Discord. There are lots of good first issues. People are happy to help you out. Would love to get more people involved. Thank you to anyone who's used ZIO. We've obviously, we've gone through a lot of iterations to get there. Things have worked, things that haven't, a lot of feedback along the way. So really appreciate everyone who's been with us. And then I'd also like to thank John for his leadership in the community and kind of being guy who made a lot of this possible. But yeah, thank you all.